Imagine a storm happens in a river system. The flow upstream might look like this, but 10-15 kilometers downstream it looks like this, a delayed and lower peak. This change in timing is called translation, and the drop in peak is known as attenuation. The tool we use to predict these changes is called flow routing. Over the next few minutes you will get a clear grasp of flow routing, its purpose, its types, and also the core methods to analyze flood wave behavior. So what is flow routing? It is simply the process of predicting how a flood wave moves, spreads, and transforms as it travels through a system. That system could be a river reach, reservoir, detention basin, or any other part of a drainage network. To model this, we have two major families of routing methods: hydraulic routing and hydrologic routing. The hydraulic routing is the high-resolution approach. It solves the full Sandvenon equations, which are based on conservation of mass and conservation of momentum. This method captures complex hydraulics like backwater effects, tidal influences, flow reversals, breach constrictions, and rapidly varied flow. It's extremely accurate, but it requires detailed cross-sections, roughness coefficients, boundary conditions, and significant computational effort. In other words, powerful but data hungry. The hydrologic routing, on the other hand, is simpler, faster, and more widely used in engineering design. It only relies on conservation of mass. Inflow minus outflow is equal to changes in storage over a certain period of time. We treat the system like a black box, and the key is to define the relationship between inflow, outflow, and storage. Since it needs far less data, hydrological routing is ideal for design storms, preliminary sizing, flood estimation studies, and systematic analysis through spreadsheets or models such as RORB, HEC-HMS, and WBNM. The hydrologic routing comes in two main methods: the reservoir routing and the channel routing. The reservoir routing is the one that we use for retarding basins, dams, and detention ponds. Here, the water surface is assumed to be horizontal. This means the storage directly depends on the water level, which also determines the outflow. So we can say the storage is a function of outflow. The most common technique for reservoir routing is level pool routing, a step-by-step method that utilizes the reservoir's storage outflow curve and the inflow hydrograph to compute how the water surface rises and how outflow increases over time. The channel routing is used for rivers and channels. There, the water surface is sloped, so the storage is influenced by both inflow and outflow. This creates two components of storage: prism storage related to outflow and the wedge storage related to the changes in the inflow. So storage becomes a function of both inflow and outflow. The most widely used method here is the Muskingum method. The Muskingum storage can be calculated by this equation, where K is the travel time through the reach. A larger K results in more attenuation, which gives a flatter hydrograph. On the other hand, X is a weighting factor, controls the balance between inflow and outflow storage. By tweaking K and X, we can model both how the flood wave moves and how it flattens as it travels downstream. In the next few videos, we will dive deep into the fundamentals of level pool routing and the Muskingum method. Then we will go through a few practical examples step by step. These hands-on tutorials will help you for flood modeling, drainage design projects, and university assignments. Stay tuned.